Picture this. You're standing at the edge of our solar system, gazing back at Earth as nothing more than a pale blue dot suspended in the cosmic void. The journey that brought you here didn't take decades or centuries like every space mission we've ever attempted. Instead, you traveled from Earth to the outer reaches of our solar system in just 3 weeks. Not through some fantastical warp drive or hyperspace jump from science fiction, but using the most powerful propulsion technology our universe has to offer. A technology so potent that a single gram contains more energy than a nuclear bomb, yet so precise it could propel humanity to the stars themselves. Tonight, we're diving deep into the extraordinary world of antimatter engines, the most powerful space technology ever imagined by human minds. What we're about to explore together isn't just another incremental improvement in rocket technology. We're talking about a fundamental breakthrough that would make our current space capabilities look like stone tools compared to supercomputers. While NASA's most advanced ion drives can achieve specific impulses of around 3,000 seconds, antimatter engines could theoretically reach specific impulses exceeding 10 million seconds. To put that in perspective, that's the difference between walking across your neighborhood and traveling at nearly half the speed of light. The physics behind this extraordinary capability lies in the most perfect energy conversion process known to science. When antimatter encounters ordinary matter, something remarkable happens that defies our everyday experience of how energy works. These particles don't just react or combine like chemical fuels burning in a rocket engine. They don't even release energy through nuclear fusion, like the processes powering our sun. Instead, they annihilate completely, converting 100% of their mass directly into pure energy according to Einstein's famous equation, E equals mc squared. Let me help you grasp just how extraordinary this energy density really is. The chemical reactions powering our most advanced rockets today convert less than 1/1000th of their fuel mass into usable energy. Nuclear fusion, the process that lights up stars and represents our most powerful energy source, converts about 0.7% of fuel mass into energy. But antimatter annihilation converts every single atom, every last bit of mass, into energy with perfect efficiency. This means antimatter contains approximately 10 billion times more energy per kilogram than the hydrogen and oxygen combustion that launched the space shuttle, and roughly 300 times more energy than nuclear fusion reactions. The implications of this energy density become truly staggering when you consider what it means for space travel. Current missions to Mars require launch windows that occur only every 26 months, when the planets align favourably, and even then the journey takes between 6 and 9 months using our best chemical propulsion systems. An antimatter engine could potentially reduce that journey time to just a few weeks, regardless of planetary alignment. The 9.5-year odyssey that NASA's New Horizons probe required to reach Pluto could be compressed into 3.5 weeks with antimatter propulsion. But the revolutionary potential of antimatter engines extends far beyond just faster travel times within our solar system. These propulsion systems could theoretically accelerate spacecraft to velocities approaching 40% of the speed of light. At such speeds, interstellar travel transforms from a multi-generational endeavour spanning thousands of years into journeys that could be completed within a human lifetime. The nearest star system, Alpha Centauri, lies about 4.25 light-years from Earth. With conventional chemical propulsion, reaching this destination would require roughly 70,000 years. Even our most optimistic fusion rocket concepts would need several thousand years to make this journey. An antimatter engine operating at peak theoretical performance would complete the same voyage in approximately 10 years. Understanding how antimatter engines could achieve such extraordinary performance requires diving into the fundamental physics of matter and antimatter annihilation. Antimatter represents the mirror image of ordinary matter, with each antimatter particle carrying the opposite electric charge of its matter counterpart. An antiproton carries a negative charge instead of the positive charge of a normal proton. A positron carries a positive charge rather than the negative charge of an electron. When these opposite particles encounter each other, they undergo complete mutual annihilation, disappearing entirely and releasing their combined mass as pure energy. This annihilation process produces a shower of high-energy particles, including gamma rays, charged pions, muons, electrons, and positrons, all traveling at velocities approaching the speed of light. The key to antimatter propulsion lies in channeling these energetic particles through magnetic nozzles to create thrust. Unlike chemical rockets that rely on heating and expanding gases, or even nuclear rockets that use fission or fusion to heat propellant, antimatter engines can directly harness the kinetic energy of annihilation products for propulsion. The theoretical architecture of antimatter propulsion systems involves several sophisticated components working in perfect harmony. Magnetic storage rings must contain the antimatter fuel using powerful electromagnetic fields, preventing any contact with ordinary matter until the precise moment when annihilation is desired for energy production. When thrust is needed, carefully controlled amounts of antimatter are released from storage to collide with ordinary matter in a reaction chamber designed to withstand temperatures exceeding those found in stellar cores. The energy released during annihilation must be captured and directed through magnetic rocket nozzles that function similarly to the particle accelerators used in modern physics laboratories. These magnetic nozzles channel the high-energy particles produced by annihilation into a directed exhaust stream, generating thrust through the same principles that govern all rocket propulsion, just at energy levels that dwarf anything we've achieved before. Different antimatter engine configurations offer varying levels of performance and complexity, representing different approaches to harnessing the incredible energy of matter-antimatter annihilation. The most conservative design, known as a solid-core antimatter engine, injects antimatter into a solid reactor core where annihilation occurs, heating the core material to extremely high temperatures. This heated core then transfers thermal energy to a propellant, which expands through a conventional rocket nozzle to produce thrust. While this approach is similar to nuclear thermal rockets, the vastly superior energy density of antimatter allows for much higher performance, even with this conservative configuration. More advanced designs eliminate the temperature limitations imposed by solid materials by using gaseous reactor cores. These gas core antimatter engines substitute low melting point solids with high temperature gas or plasma, permitting much higher operational temperatures and correspondingly better performance. The gaseous core system removes traditional heating elements altogether, directly injecting antimatter into the reaction mass stream and using magnetic fields to confine the charged reaction products while heating the propellant. Plasma core configurations push antimatter engine performance even further by converting the propellant itself into plasma. These systems inject enough antimatter to ionize the reaction mass completely, creating a plasma exhaust that can achieve specific impulses as high as 1 million seconds using hydrogen as propellant. However, these advanced designs require sophisticated magnetic confinement systems, since conventional combustion chambers and rocket nozzles can no longer withstand the extreme conditions involved. The ultimate expression of antimatter propulsion technology is the beam core or pion rocket, which aims for complete matter-antimatter annihilation. These engines use equal amounts of matter and antimatter fuel, resulting in total annihilation of all nucleons and antinucleons to generate a pure pion exhaust. When antiprotons annihilate with protons, they produce charged particles that can be funneled through magnetic nozzles to generate thrust with extraordinary efficiency. Theoretically, such systems could achieve exhaust velocities approaching significant fractions of the speed of light, with specific impulses exceeding 30 million seconds. The potential applications of antimatter propulsion technology would fundamentally transform every aspect of space exploration and development. Missions to the outer planets, currently requiring decades of travel time and complex gravitational assist maneuvers, could be completed in weeks or months with direct trajectories. The asteroid belt, which represents an enormous reservoir of mineral resources that could supply human civilization for millennia, would become as accessible as Earth orbit is today. Perhaps most significantly, antimatter engines could make interstellar exploration a practical reality rather than a distant dream. Robotic probes powered by antimatter could reach nearby star systems within decades, potentially discovering habitable worlds or even signs of extraterrestrial life within the lifetime of the scientists who designed and launched them. Human missions to other star systems, while still representing enormous challenges, would transition from impossible fantasies to engineering problems that could potentially be solved with sufficient technological development and resources. The energy density of antimatter also opens possibilities for space-based infrastructure projects on scales we can barely imagine today. Massive space habitats housing millions of people, interplanetary cargo transportation networks, asteroid mining operations, and even the construction of artificial worlds become conceivable when you have access to energy sources measured in terms of complete mass conversion rather than chemical or nuclear reactions. However, the path from theoretical possibility to practical reality involves overcoming technical challenges that push the boundaries of human engineering capabilities. The production, storage, and controlled use of antimatter represents some of the most difficult problems in applied physics, requiring solutions to fundamental questions about containing and manipulating matter's most energetic opposite. Current antimatter production occurs primarily at advanced particle physics laboratories like CERN, where sophisticated particle accelerators can create tiny quantities of antiprotons and positrons through high-energy collisions. But the scale of current production efforts provides sobering perspective on the challenges ahead. The entire global antimatter production capacity amounts to roughly 10 nanograms per year, enough to power a small light bulb for just a few minutes. Creating the kilogram quantities of antimatter needed for practical space propulsion would require production increases of more than 10 orders of magnitude. The energy requirements for antimatter production present another formidable barrier to practical applications. Creating antimatter requires input energies at least equivalent to the rest mass energy of the created particles, and typically millions of times more, due to inefficiencies in current production methods. Generating a single gram of antimatter would consume approximately 25 million kilowatt-hours of energy, enough electricity to supply a small city for an entire year at current energy costs exceeding $4 million. Even more challenging than production is the problem of antimatter storage and containment. Since antimatter annihilates instantly upon contact with any ordinary matter, it must be suspended in perfect vacuum using electromagnetic fields, never touching the walls of any material container. Current storage systems use sophisticated devices called penning traps, which employ carefully controlled electric and magnetic fields to suspend individual antiparticles away from all matter surfaces. The longest successful antimatter storage demonstration achieved containment for only 16 minutes, and even that involved just a few individual atoms rather than the grams or kilograms required for spacecraft propulsion. And if you find yourself drawn to these cosmic puzzles, I'd be grateful if you gave this video a like and perhaps subscribe. Advanced storage concepts envision condensing antimatter into solid crystalline forms maintained at temperatures approaching absolute zero, suspended by superconducting magnetic fields in ultra-high vacuum chambers. Such systems would need to operate reliably for months or years while maintaining perfect containment of substances more explosive than any material humans have ever handled. Despite these enormous challenges, the fundamental physics underlying antimatter propulsion contains no violations of known natural laws. Every component required for antimatter engines, from magnetic confinement systems to particle beam focusing devices, represents extensions of technologies already demonstrated in laboratory environments. The engineering challenges are immense, but they appear to be problems of scale and precision rather than fundamental impossibilities. Modern research efforts are making steady progress toward overcoming the barriers to practical antimatter applications. Recent advances in antimatter storage technology have extended containment times from minutes to hundreds of days for antiprotons, representing improvements of several orders of magnitude over previous capabilities. Specialized companies are developing more efficient production methods specifically designed for propulsion applications rather than fundamental physics research. NASA has officially recognized antimatter propulsion as a critical technology for future space exploration, including it in their advanced propulsion research programs alongside other breakthrough concepts like fusion rockets and solar sails. The recognition by the world's premier space agency indicates that antimatter propulsion has transitioned from pure science fiction to serious engineering research, even if practical applications remain years or decades in the future. The historical development of antimatter propulsion concepts traces back to the early days of both space exploration and particle physics. Austrian aerospace engineer Eugen Sanger pioneered these ideas in the 1950s, proposing photon rockets that would use antimatter annihilation to produce directed energy beams for propulsion. Although his early concepts contained flaws due to incomplete understanding of antimatter physics at the time, Sanger established the theoretical foundation for all subsequent antimatter propulsion research. As our understanding of antimatter physics has advanced, so too have the sophistication and realism of proposed engine designs. Modern computer simulations using advanced computational tools can model the complex physics of antimatter annihilation and magnetic field interactions with unprecedented accuracy, allowing engineers to optimize engine parameters for maximum performance while identifying potential solutions to practical engineering challenges. The convergence of advancing antimatter physics, improving magnetic confinement technology, and growing investment in breakthrough propulsion research suggests that antimatter engines may transition from laboratory curiosities to practical propulsion systems sooner than many experts previously believed possible. While significant technical hurdles remain, the potential rewards of success are so extraordinary that research efforts continue to intensify around the world. As we stand on the threshold of this revolutionary technology, we're witnessing the early stages of what could become the most significant advancement in transportation since the invention of powered flight. The antimatter engines we've explored tonight represent more than just faster rockets or more efficient propulsion systems. They embody humanity's potential to transcend the limitations that have confined us to a single planet, opening pathways to cosmic destinations that have existed only in our imagination. But mastering the incredible power of antimatter annihilation requires solving some of the most complex engineering challenges our species has ever attempted. The technical obstacles ahead are formidable, the energy requirements staggering, and the precision demanded unprecedented in human technology. Yet the path to harnessing this cosmic force begins with one of the most challenging manufacturing problems humanity has ever confronted. Creating antimatter requires us to reverse the fundamental processes that built our universe, artificially generating particles that nature seems designed to eliminate. Every antiproton that exists today was painstakingly created in the heart of a particle accelerator, where beams of ordinary protons are smashed into target materials at velocities approaching the speed of light. The physics of antimatter production relies on Einstein's mass-energy equivalence, working in reverse. Instead of converting mass to energy through annihilation, we must convert enormous amounts of energy back into matter and antimatter pairs. When high-energy protons collide with atomic nuclei in particle accelerator targets, the kinetic energy of these collisions can spontaneously create new particle pairs, including the antiprotons we desperately need for future propulsion systems. But the inefficiency of this process defies comprehension. For every billion joules of energy we pump into particle accelerators, we might capture just a few millionths of a joule worth of usable antimatter. The rest vanishes as heat, scattered particles, and electromagnetic radiation that serves no useful purpose for our engineering goals. Current production methods at facilities like CERN require approximately 10 trillion times more energy input than the antimatter output can theoretically provide, making the economic case for antimatter propulsion seem impossible under today's technological constraints. The European Organisation for Nuclear Research operates the most sophisticated antimatter production facility on Earth, generating roughly 10 nanograms of antiprotons annually through their complex network of particle accelerators and storage rings. To put this microscopic quantity in perspective, 10 nanograms represents approximately 60 billion individual antiprotons. While this might sound like an enormous number, the total mass involved is so small that it would take 100 billion years of continuous production at current rates to accumulate just 1 gram of antimatter fuel. The antiproton decelerator at CERN represents the pinnacle of current antimatter manufacturing technology, capturing antiprotons from high-energy collisions and gradually slowing them down through a series of cooling stages until they can be trapped and stored. This process requires exquisite precision, since antiprotons moving too quickly cannot be contained by magnetic fields, while those moving too slowly risk annihilating with stray atoms in the vacuum chambers before they can be captured. Recent advances in antimatter production have focused on improving the efficiency of each step in this complex manufacturing process. Researchers have developed new target materials that produce higher yields of antiprotons per collision, along with improved cooling techniques that can capture a larger fraction of the antiprotons generated during each production run. Some experimental approaches use laser cooling and electromagnetic focusing to increase capture rates by factors of 10 or more compared to earlier methods. The cooling process itself represents a marvel of precision engineering that operates at the intersection of quantum mechanics and classical electromagnetics. Newly created antiprotons emerge from collision events with enormous kinetic energies, moving at significant fractions of light speed in random directions. Magnetic focusing systems must first collect these scattered particles into coherent beams, then gradually reduce their velocities through interactions with carefully controlled electric and magnetic fields. Sympathetic cooling techniques have emerged as one of the most promising approaches for improving antimatter production efficiency. In these systems, antiprotons are mixed with laser-cooled ordinary particles in magnetic traps, allowing the cold particles to absorb kinetic energy from the hot antiprotons through electromagnetic interactions. This process can reduce antiproton temperatures from millions of degrees to just a few thousandths of a degree above absolute zero, making them much easier to trap and store for extended periods. The energy economics of antimatter production reveal the magnitude of the challenge facing practical applications. Creating 1 gram of antimatter using current methods would require approximately 25 million kilowatt-hours of electrical energy, roughly equivalent to the annual electricity consumption of 2,000 average American homes. At current industrial electricity rates, this represents an energy cost exceeding $4 million per gram, before accounting for the enormous infrastructure costs of particle accelerators and storage systems. However, These sobering economics reflect the inefficiencies of production systems designed for fundamental physics research rather than industrial manufacturing. Current particle accelerators were built to study the properties of subatomic particles, not to optimize antimatter yield per unit of energy input. Dedicated antimatter production facilities could potentially achieve much higher efficiencies through designs optimized specifically for manufacturing rather than scientific investigation. Theoretical studies suggest that purpose-built antimatter factories could improve production efficiency by factors of hundreds or thousands compared to current research facilities. These hypothetical systems would use superconducting accelerators operating at much higher beam intensities than existing machines, coupled with advanced target designs that maximize antiproton yield while minimizing energy waste through unwanted particle interactions. The development of such dedicated production facilities would require investments comparable to major infrastructure projects, like transcontinental railroad networks or interstate highway systems. But the potential returns could justify these enormous costs if antimatter propulsion proves capable of opening economic opportunities in space that dwarf any terrestrial industry. Access to asteroid belt mineral resources alone could generate economic value measured in quadrillions of dollars, making even trillion-dollar investments in antimatter infrastructure economically viable. Storage and containment of antimatter present equally formidable challenges that push the boundaries of precision engineering and materials science. Unlike any other fuel in human experience, antimatter cannot be stored in conventional containers since it annihilates instantly upon contact with ordinary matter. Every atom of antimatter must remain suspended in perfect isolation from all material surfaces, contained only by invisible electromagnetic forces that never fail or fluctuate. Penning traps represent the current state-of-the-art in antimatter containment technology, using combinations of electric and magnetic fields to create three-dimensional potential wells that can hold charged particles indefinitely in principle. These devices function like electromagnetic bottles, with field configurations that keep antiprotons or positrons trapped in tiny volumes of ultra-high vacuum space. The magnetic fields must be precisely shaped to prevent particle losses, while electric fields provide the fine control needed to manipulate individual antiparticles with atomic precision. The longest successful antimatter storage experiment at CERN maintained antiproton confinement for over 400 days, representing a dramatic improvement from earlier attempts that lost particles within minutes or hours. This achievement required maintaining magnetic field stability better than 1 part in a billion, while operating the entire system in vacuum conditions more perfect than the space between galaxies. Even microscopic vibrations or electromagnetic interference could disrupt the delicate field configurations and cause immediate loss of the stored antimatter. Scaling these storage technologies to practical propulsion applications presents challenges that dwarf current laboratory demonstrations. Instead of storing a few hundred antiprotons for scientific study, spacecraft would need to contain kilograms of antimatter for months or years during interplanetary journeys. The containment systems would need to operate reliably in the harsh environment of space, subject to cosmic radiation, temperature extremes, and the mechanical stresses of acceleration and maneuvering. Advanced storage concepts envision condensing antimatter into solid crystalline forms that could achieve much higher storage densities than current gas phase containment methods. Theoretical calculations suggest that antihydrogen atoms could be cooled and compressed into solid structures similar to metallic hydrogen, held together by quantum mechanical forces while suspended in magnetic fields. Such antihydrogen ice could potentially store thousands of times more antimatter per unit volume compared to current trap-based systems. The magnetic levitation systems required for solid antimatter storage would need to generate field strengths exceeding those of any existing technology. Superconducting electromagnets operating at temperatures near absolute zero could provide the necessary field intensities, but maintaining such extreme conditions in space would require sophisticated cryogenic systems with unprecedented reliability and efficiency. Any failure of the cooling systems could cause immediate loss of magnetic containment and catastrophic annihilation of the stored fuel. Electromagnetic storage rings offer another approach to antimatter containment that could potentially scale to larger quantities. These systems, similar to the particle accelerator rings used in physics laboratories, would circulate anti-proton beams in carefully controlled magnetic orbits. By storing antimatter in motion rather than at rest, ring systems could contain larger quantities while maintaining the precise field control needed to prevent particle losses. The engineering challenges of antimatter storage extend far beyond the electromagnetic containment systems themselves. Spacecraft carrying antimatter fuel would need multiple independent backup systems for every critical component, since any single failure could result in complete loss of the stored fuel through annihilation. The safety systems would need to detect and respond to potential failures faster than human reaction times, using automated systems that could isolate and safely dispose of antimatter in emergency situations. Radiation shielding represents another critical challenge for antimatter storage systems. The gamma rays produced by any accidental annihilation events would be energetic enough to damage electronic systems and pose serious health risks to nearby crew members. Spacecraft designs would need to incorporate heavy shielding around antimatter storage areas, adding mass that reduces the performance advantages of antimatter propulsion while creating complex engineering trade-offs. The precision required for antimatter containment also creates vulnerability to external disturbances that would have no effect on conventional spacecraft systems. Electromagnetic interference from solar storms or nearby electrical equipment could disrupt the delicate field configurations needed for particle confinement. Even gravitational effects from massive celestial bodies could potentially influence antimatter trajectories enough to cause containment failures in poorly designed systems. Despite these formidable challenges, recent advances in superconducting technology, precision electromagnetics, and automated control systems suggest that practical antimatter storage may be achievable with sufficient development effort. High-temperature superconductors, discovered in recent decades, could enable more efficient magnetic field generation, while advances in computational control systems could provide the real-time precision needed to maintain containment under dynamic conditions. The propulsion efficiency advantages of antimatter engines become truly extraordinary when compared to any other form of space transportation ever conceived or demonstrated. Traditional chemical rockets achieve exhaust velocities of approximately 4,000 meters per second, limited by the molecular bonds that hold chemical compounds together. Nuclear thermal rockets can potentially reach exhaust velocities of 8 to 10,000 meters per second by using nuclear fission to heat hydrogen propellant. Even theoretical fusion rockets might achieve exhaust velocities approaching 100,000 meters per second. Antimatter engines, by contrast, could theoretically accelerate exhaust particles to velocities approaching the speed of light itself, roughly 300 million meters per second. This represents an improvement of several thousand times over chemical rockets and hundreds of times better than even the most optimistic fusion propulsion concepts. The specific impulse of antimatter engines, measured in seconds of thrust per unit weight of propellant, could exceed 10 million seconds compared to the few hundred seconds achieved by chemical rockets. The physics underlying these extraordinary performance capabilities stems from the fundamental nature of antimatter annihilation reactions. When antiprotons collide with protons, they produce charged pions that naturally travel at velocities approaching significant fractions of light speed. These high-energy particles can be channeled through magnetic nozzles to create thrust, bypassing the thermal limitations that constrain all other rocket technologies. Beam core antimatter engines represent the ultimate expression of this propulsion concept, aiming to harness the complete annihilation energy through direct acceleration of charged particles. In these theoretical systems, equal amounts of matter and antimatter fuel undergo total annihilation, converting their entire mass into kinetic energy of the exhaust stream. Computational simulations suggest such engines could achieve specific impulses exceeding 30 million seconds while maintaining thrust levels sufficient for practical spacecraft acceleration. The efficiency advantages of antimatter propulsion enable mission profiles that are simply impossible with any other technology. Current Mars missions must follow carefully planned transfer orbits that minimize energy requirements, taking advantage of planetary motion to reduce the velocity changes needed for interplanetary travel. These trajectory constraints force mission durations of 6 to 9 months and restrict launch opportunities to narrow windows that occur only every 26 months. Antimatter spacecraft could ignore these constraints entirely, following direct trajectories between planets, regardless of their orbital positions. The enormous energy density of antimatter fuel makes the additional velocity requirements irrelevant compared to the fuel mass limitations that govern conventional missions. Mars journeys could be completed in 3 to 4 weeks using constant acceleration profiles that would provide artificial gravity for crew comfort during the transit. The outer solar system, currently accessible only through multi-year voyages requiring complex gravitational assist maneuvers, would become as reachable as the Moon is today. Jupiter could be reached in 6 weeks, Saturn in 2 months, and even distant Pluto in less than 4 months of travel time. These reduced journey durations would transform planetary science by enabling regular cargo deliveries and crew rotations to research stations throughout the solar system. Interstellar missions represent perhaps the most compelling application of antimatter propulsion technology. Current space probe velocities achieved through gravitational assists from multiple planetary encounters reach at most 20 kilometers per second relative to the Sun. At these speeds, reaching the nearest star would require over 20,000 years of travel time, making interstellar exploration impossible within any reasonable planning horizon. Antimatter engines could accelerate spacecraft to velocities measured in significant percentages of light speed, reducing interstellar journey times to decades rather than millennia. A probe traveling at 10% of light speed could reach Alpha Centauri in approximately 40 years, making it possible to receive scientific data from another star system within a human lifetime. More aggressive mission profiles using 20 or 30% of light speed could complete the same journey in 15 to 20 years. The acceleration capabilities of antimatter engines would also revolutionize spacecraft operations within individual planetary systems. Current spacecraft must coast unpowered for most of their journeys, making course corrections expensive in terms of fuel consumption and mission duration. Antimatter spacecraft could maintain continuous acceleration throughout their missions, enabling rapid response to changing scientific priorities or emergency situations. Cargo transportation throughout the solar system would become economically viable for the first time, opening possibilities for industrial development that are impossible under current transportation constraints. Asteroid mining operations could ship raw materials to Earth orbit or Mars colonies using antimatter-powered cargo vessels that complete round trips in weeks rather than years. The reduced transportation costs could make space-based manufacturing competitive with terrestrial production for many specialized applications. The military implications of antimatter propulsion technology would be equally revolutionary, creating strategic capabilities that fundamentally alter the balance of power in space. Antimatter-powered interceptors could respond to ballistic missile launches within minutes rather than hours, potentially enabling defensive systems that could neutralize nuclear threats before they reach their targets. Space-based platforms using antimatter propulsion could maintain persistent coverage of any location on Earth, fundamentally changing the nature of military surveillance and reconnaissance. However, the same technologies that enable peaceful exploration could also create weapons of unprecedented destructive capability. Antimatter warheads would release energies comparable to thermonuclear weapons, while producing much less radioactive fallout, potentially making them attractive for military applications. The dual-use nature of antimatter technology raises profound questions about proliferation control and international governance that have no precedent in human experience. The economic implications of practical antimatter propulsion extend far beyond the space transportation sector itself. Rapid access to asteroid belt resources could provide virtually unlimited supplies of rare earth elements, platinum group metals, and other materials that are scarce on Earth but abundant in space. The economic value of a single metallic asteroid could exceed the gross domestic product of major nations, making the development costs of antimatter infrastructure seem modest by comparison. Space-based solar power becomes practically achievable when construction materials can be transported from lunar or asteroid sources using antimatter cargo vessels. Massive solar collectors built in space from extraterrestrial materials could beam clean energy to Earth using microwave transmission, potentially solving climate change while providing abundant power for continued antimatter production. The positive feedback loop between antimatter-enabled resource extraction and expanded antimatter production capacity could drive exponential growth in space-based economic activity. Manufacturing in space offers advantages that become compelling when transportation costs drop to levels achievable with antimatter propulsion. The vacuum and microgravity environment enable production techniques impossible on Earth, particularly for advanced materials like perfect crystals, ultra-pure pharmaceuticals, and exotic alloys. Products manufactured in space using asteroid-derived raw materials could be delivered to Earth markets more cheaply than equivalent goods produced terrestrially. The biological sciences would benefit enormously from access to the pristine vacuum and radiation environment of deep space. Long-duration biological experiments could be conducted in isolation from Earth's complex ecosystem, enabling research into the fundamental mechanisms of life that are impossible to study in terrestrial laboratories. The search for extraterrestrial life would accelerate dramatically when sample return missions to potentially habitable worlds become feasible within reasonable timeframes. Terraforming projects that seem impossible under current technological constraints could become achievable with antimatter-powered transportation systems. Moving massive quantities of atmospheric gases between planets, redirecting comets to provide water for arid worlds, or constructing orbital mirrors to modify planetary climates all become engineering problems rather than impossibilities when energy and transportation constraints are removed. The scientific research enabled by antimatter propulsion would advance human knowledge across virtually every field of investigation. Direct exploration of the outer solar system and interstellar space would provide unprecedented insights into planetary formation, stellar evolution, and the distribution of life throughout the galaxy. High-energy physics experiments conducted in the deep space environment could probe fundamental questions about the nature of space, time, and matter itself. Yet for all these extraordinary possibilities, the development of practical antimatter propulsion systems requires overcoming technical challenges that push every aspect of human engineering capability to its absolute limits. The precision required for antimatter production, storage, and controlled annihilation exceeds anything achieved in previous technological endeavors. The energy densities involved in antimatter reactions create safety hazards that have no precedent in human experience, requiring entirely new approaches to risk management and system design. The materials science challenges alone represent decades of fundamental research and development, Containing and channeling the products of antimatter annihilation requires materials that can withstand temperatures exceeding those found in stellar cores, while maintaining structural integrity under electromagnetic stresses that would instantly vaporize conventional engineering materials. Superconducting electromagnets must operate reliably for years, while generating magnetic fields stronger than any produced on Earth, all while maintaining the precise field geometries needed for particle confinement. The computational challenges of controlling antimatter systems in real time require advances in processing power and software sophistication that exceed current capabilities by orders of magnitude. Every aspect of antimatter engine operation must be monitored and controlled with microsecond precision, responding to changing conditions faster than any human operator could possibly react. The control algorithms must account for complex interactions between electromagnetic fields, particle dynamics, and thermodynamic processes that operate simultaneously across vastly different time and length scales. International cooperation on the scale of the International Space Station or Large Hadron Collider would be essential for developing antimatter propulsion technology within reasonable timeframes. No single nation possesses the financial resources and technical expertise needed to master every aspect of antimatter engineering independently. Collaborative research programs involving the world's leading scientific institutions could accelerate progress while sharing the enormous development costs among multiple stakeholders. The regulatory and safety frameworks governing antimatter technology development require entirely new approaches to risk assessment and management. Traditional safety analysis methods designed for chemical and nuclear technologies are inadequate for systems involving complete mass energy conversion. International treaties and oversight mechanisms must be established before antimatter technology becomes widely available, preventing proliferation to hostile actors while enabling peaceful development. Public acceptance of antimatter technology will require extensive education and outreach efforts to address legitimate safety concerns while communicating the extraordinary benefits that successful development could provide. The association of antimatter with science fiction weapons and doomsday scenarios creates psychological barriers that must be overcome through transparent communication about the actual risks and safeguards involved in practical applications. The timeline for achieving practical antimatter propulsion depends critically on the level of investment and international cooperation that can be sustained over the decades required for development. Optimistic projections suggest that small-scale demonstration systems could be achieved within 20 to 30 years, given sufficient funding and technical focus. Practical spacecraft applications would follow within another decade or two, assuming that fundamental technical barriers prove surmountable. Conservative estimates extend these timelines significantly, acknowledging the unprecedented nature of the challenges involved and the likelihood of encountering unexpected technical obstacles. Some aspects of antimatter technology may require breakthrough discoveries in fundamental physics or materials science that cannot be scheduled or predicted with confidence. The development pathway could resemble the Manhattan Project or Apollo program in its scope and urgency, requiring sustained national commitment over extended periods. The investment requirements for antimatter propulsion development would rival the largest technological projects in human history. Initial research and development costs could exceed $100 billion before the first practical demonstration systems become operational. Production infrastructure capable of manufacturing kilogram quantities of antimatter would require additional investments of similar magnitude, creating total program costs comparable to major military procurement programs or infrastructure megaprojects. However, these enormous upfront costs must be evaluated against the potential economic returns from successful development. Access to space resources enabled by antimatter propulsion could generate economic value measured in quadrillions of dollars over the following centuries. The return on investment timeline may span generations, but the magnitude of potential returns could justify even the largest conceivable development investments. Private sector involvement in antimatter research has begun accelerating as entrepreneurial companies recognize the transformational potential of the technology. Startup companies are developing improved production methods, advanced storage concepts, and specialized components that could support larger development efforts. While private funding cannot support the full scale of development required, these smaller efforts could provide crucial technological building blocks for future government-sponsored programs. The convergence of advancing scientific understanding, improving engineering capabilities, and growing recognition of antimatter's potential suggests that we may be approaching a tipping point where serious development efforts become inevitable. The combination of climate change pressures, resource scarcity concerns, and renewed interest in space exploration creates powerful motivations for pursuing breakthrough propulsion technologies that seemed purely academic just decades ago. As we stand at the threshold of potentially the greatest transportation revolution in human history, the antimatter engines we've explored tonight represent more than just theoretical physics or engineering speculation. They embody humanity's perpetual drive to transcend the limitations that confine us, to reach beyond the boundaries of what seems possible, and to unlock the vast potential that lies waiting among the stars. The technical challenges ahead are unprecedented in their complexity and scope, requiring advances across every field of science and engineering. Yet the potential rewards, measured not just in scientific knowledge or economic value, but in the expansion of human consciousness across the cosmos, justify efforts on scales that dwarf any previous technological endeavor. The antimatter age may still lie years or decades in the future, but the foundation for that extraordinary transformation is being laid today in laboratories and research facilities around the world. The universe awaits, and antimatter may provide the key to unlocking its infinite possibilities. The engineering precision required for antimatter engines extends into realms of manufacturing tolerance that challenge our understanding of what's physically achievable. Consider the magnetic field uniformity needed to contain antimatter plasma during the annihilation process. Current superconducting magnets can maintain field stability to within 1 part per million over short periods, but antimatter engines would require field variations of less than 1 part per billion sustained for months or years of continuous operation. This represents an improvement in precision comparable to the difference between measuring distances with a ruler versus detecting the width of individual atoms. The materials engineering challenges become even more daunting when you examine what happens inside an operating antimatter engine. During peak operation, the reaction chamber experiences temperatures exceeding 100 million degrees Celsius, hot enough to vaporize any known material instantly. The charged particles streaming from annihilation events carry kinetic energies measured in billions of electron volts, creating radiation fluxes that would destroy conventional electronics within microseconds. The magnetic containment systems must somehow channel these impossibly energetic particles while protecting themselves from destruction by the very forces they're attempting to control. Advanced computational modeling reveals the intricate dance of electromagnetic forces required to make antimatter propulsion work in practice. The magnetic nozzles that focus annihilation products into directed thrust must shape and control particle beams with precision that exceeds our most sophisticated particle accelerators. Unlike laboratory accelerators that operate in carefully controlled environments, spacecraft magnetic nozzles must function reliably while subject to the thermal cycling, radiation exposure, and mechanical stresses of space travel. The software systems controlling these electromagnetic interactions require processing capabilities that push beyond current computational limits. Real-time particle trajectory calculations must account for millions of individual particle interactions occurring every microsecond, with control algorithms responding faster than the speed of light allows signals to travel between different parts of the engine. The computational load resembles running detailed weather simulations for entire planets, except the calculations must be completed thousands of times per second to maintain stable engine operation. Thermal management in antimatter engines presents paradoxes that seem to violate common engineering intuition. While the annihilation reaction produces temperatures comparable to stellar cores, the engine must simultaneously maintain superconducting electromagnets at temperatures near absolute zero, just meters away from the reaction zone. The thermal isolation systems must prevent any heat transfer between these extreme temperature regions, while allowing electromagnetic fields to pass through unimpeded. Current thermal protection concepts involve nested layers of superconducting shields, each maintained at progressively lower temperatures through sophisticated cryogenic cooling systems. The coolant systems themselves represent marvels of engineering that operate at the theoretical limits of thermodynamic efficiency. Liquid helium circulators must function continuously for years without maintenance, while exposed to intense radiation fields that would quickly degrade conventional mechanical components. The cooling power requirements exceed those of entire cities, yet must be provided by systems compact enough to fit aboard spacecraft with severe mass limitations. Advanced heat exchanger designs use magnetic levitation to eliminate mechanical contact between moving parts, reducing wear while enabling operation in the harsh electromagnetic environment surrounding the antimatter reaction zone. Quality control in antimatter production requires analytical techniques that can verify the purity and composition of individual atoms. Unlike conventional fuels where chemical analysis can detect impurities at the parts per million level, antimatter contamination must be measured in terms of individual unwanted particles among trillions of desired ones. Spectroscopic analysis of trapped antimatter requires laser systems with wavelength stability better than 1 part in a trillion, enabling identification of specific antimatter isotopes through their quantum mechanical energy signatures. The production facilities needed for practical antimatter manufacturing would dwarf any existing industrial infrastructure in terms of both scale and precision. Dedicated antimatter factories might require particle accelerator complexes spanning hundreds of square kilometers with superconducting beamlines maintained in perfect alignment despite thermal expansion, seismic activity, and gravitational tidal forces. The electrical power requirements could exceed the output of major nuclear power plants, demanding dedicated energy infrastructure designed specifically for antimatter production operations. Environmental considerations for antimatter production extend far beyond conventional industrial safety concerns. The high-energy particle beams used in antimatter creation produce secondary radiation that must be contained and shielded to protect surrounding communities. Underground facilities built in geologically stable formations could provide natural radiation shielding while minimizing the environmental footprint of large-scale antimatter production. The waste heat generated during production could potentially be captured and used for district heating or industrial processes, improving overall energy efficiency. Automated production systems would eliminate human exposure to the extreme radiation environments associated with antimatter manufacturing. Robotic systems designed specifically for high radiation environments could perform maintenance and optimization tasks that would be lethal to human workers. Machine learning algorithms could optimize production parameters in real time, adjusting beam intensities and target configurations to maximize antimatter yield while minimizing energy consumption and equipment wear. The economics of scale in antimatter production follow patterns similar to semiconductor manufacturing, where enormous upfront investments in fabrication facilities enable low per-unit costs once production volumes reach sufficient levels. The first kilogram of antimatter might cost trillions of dollars to produce, but the 1,000th kilogram could potentially be manufactured for millions of dollars as production techniques mature and facilities operate at full capacity. This cost reduction trajectory would be essential for making antimatter propulsion economically viable for commercial space transportation. International cooperation in antimatter development faces unique challenges related to the dual-use nature of the technology. While antimatter engines enable peaceful space exploration, the same production and storage technologies could potentially be adapted for weapons applications. Verification and monitoring systems would need to distinguish between peaceful and military antimatter programs without compromising legitimate research activities. International inspection regimes, similar to those governing nuclear technology, could provide confidence-building measures while preventing proliferation to hostile actors. The scientific instrumentation required for antimatter research pushes detector technology into previously unexplored territory. Particle detectors must function reliably in electromagnetic field environments, millions of times stronger than Earth's magnetic field, while measuring individual particle interactions with nanosecond timing precision. Radiation-hardened electronics must continue operating despite exposure to particle fluxes that would instantly disable conventional semiconductor devices. Advanced detector designs use diamond crystal substrates and superconducting readout systems to achieve the radiation tolerance needed for antimatter research applications. Space-based antimatter production offers intriguing possibilities for overcoming some terrestrial limitations while creating new technical challenges. Solar power satellites could provide the enormous electrical energy needed for antimatter production without requiring terrestrial power infrastructure. The vacuum environment of space eliminates atmospheric interference with particle beams while providing natural isolation from populated areas. However, the technical complexity of operating particle accelerators in space, combined with the enormous mass requirements for magnetic shielding systems, creates engineering challenges that may prove even more difficult than terrestrial production. The transportation infrastructure for moving antimatter between production facilities and launch sites represents another layer of technical complexity with no historical precedent. Antimatter storage systems must maintain perfect containment while being transported over potentially thousands of kilometers of terrestrial terrain. Vibration isolation systems must protect delicate magnetic trap configurations from road irregularities, while power systems ensure continuous operation of containment fields throughout the journey. Emergency protocols must address scenarios ranging from transportation accidents to deliberate sabotage attempts, all while preventing any possibility of accidental annihilation. Launch vehicle integration of antimatter propulsion systems creates unique challenges for spacecraft design and mission planning. The antimatter storage and engine systems must survive the mechanical stresses and acoustic environment of chemical rocket launch, while maintaining the precise field alignments needed for proper operation. Electromagnetic compatibility between antimatter systems and conventional spacecraft electronics requires extensive shielding and filtering to prevent interference. Mission timelines must account for the limited storage duration of antimatter fuel, requiring precise coordination between production, transportation, and launch operations. The testing and validation of antimatter engines demands new approaches to propulsion system development that account for the unique hazards and performance characteristics of antimatter technology. Ground-based test facilities must provide radiation shielding comparable to particle physics laboratories, while enabling thrust measurements with sufficient accuracy to validate engine performance. Remote testing sites in uninhabited regions could minimize risks to populated areas while providing realistic operational environments for system validation. Flight testing of antimatter propulsion systems would likely begin with unmanned demonstrations in deep space, far from Earth and other populated areas. Initial test flights could validate basic engine operation and performance while gathering data on system reliability and operational procedures. Progressive testing campaigns would gradually increase mission complexity and duration, building confidence in antimatter technology before attempting crewed missions. The development timeline for antimatter propulsion could span several decades, from first laboratory demonstrations to operational spacecraft systems. The maintenance and servicing requirements for antimatter engines create operational challenges unlike any previous spacecraft systems. The complexity of antimatter storage and propulsion systems would likely require specialized maintenance facilities in space, equipped with the sophisticated tools and expertise needed for system servicing. Orbital maintenance depots could extend mission duration and reliability while reducing the mass penalties associated with carrying spare parts and maintenance equipment aboard individual spacecraft. Crew training for antimatter-powered spacecraft operations would require expertise spanning multiple technical disciplines, from particle physics to electromagnetic engineering. Mission specialists would need detailed understanding of antimatter storage systems, engine operation procedures, and emergency response protocols. Simulation systems for training purposes must accurately model the complex interactions between electromagnetic fields, particle dynamics, and spacecraft systems while providing realistic scenarios for emergency response training. The psychological aspects of operating antimatter systems present unique challenges for crew selection and training. Unlike conventional spacecraft systems, where failures typically result in mission degradation or crew discomfort, antimatter system failures could potentially result in immediate catastrophic destruction of the entire spacecraft. Crew members must maintain peak performance while operating systems containing energies equivalent to nuclear weapons, requiring psychological profiles and training programs specifically designed for high-stress, high-consequence operational environments. Mission planning for antimatter-powered spacecraft must account for the unique operational characteristics and constraints of antimatter propulsion systems. Unlike chemical rockets that can operate in any orientation relative to gravitational fields, antimatter engines may require specific orientations to maintain proper magnetic field configurations. Trajectory planning must consider the continuous acceleration capabilities of antimatter engines, while ensuring that engine operation doesn't interfere with scientific instruments or communication systems through electromagnetic emissions. The insurance and liability frameworks for antimatter-powered space missions require entirely new approaches to risk assessment and coverage. Traditional space insurance models based on chemical propulsion systems cannot adequately address the unique risks associated with antimatter technology. International liability treaties must be updated to address scenarios involving antimatter system failures that could potentially affect multiple nations or orbital assets. The financial instruments needed to support antimatter mission development could require government backing due to the unprecedented nature and scale of potential risks. Regulatory approval processes for antimatter propulsion systems would likely require new institutional frameworks combining expertise from space agencies, nuclear regulatory authorities, and particle physics research organizations. Safety analysis methodologies must be developed specifically for antimatter systems, incorporating lessons learned from nuclear technology while addressing the unique characteristics of matter-antimatter annihilation. Environmental impact assessments must consider potential consequences ranging from electromagnetic interference with satellite systems to atmospheric effects from high-energy particle emissions. The supply chain for antimatter engine components spans multiple high-technology industries, from superconducting magnet manufacturers to precision electronics suppliers. Quality assurance programs must ensure that every component meets the extraordinary reliability and performance standards required for antimatter applications. Manufacturing tolerances for critical components may require advances in precision machining and measurement technology that push beyond current industrial capabilities. Intellectual property considerations in antimatter technology development create complex issues related to international technology transfer and competitive advantage. The enormous development costs and strategic importance of antimatter propulsion technology create strong incentives for protecting proprietary innovations, while potentially hindering the international cooperation needed for successful development. Licensing frameworks must balance legitimate commercial interests with the need for broad access to breakthrough technologies that could benefit all humanity. The educational infrastructure needed to support antimatter technology development requires new academic programs combining physics, engineering, and specialized technical skills that don't currently exist in traditional university curricula. Graduate programs in antimatter engineering would need to integrate theoretical particle physics with practical engineering applications while providing hands-on experience with exotic technologies. International exchange programs could facilitate knowledge sharing while building the global expertise base needed for large-scale antimatter development projects. Public engagement and science communication around antimatter technology must address both the extraordinary potential benefits and the legitimate safety concerns associated with matter-antimatter annihilation. Educational outreach programs could help build public understanding of antimatter physics while countering misconceptions derived from science fiction portrayals. Transparent communication about safety measures and risk mitigation strategies could build public confidence in antimatter technology development while maintaining appropriate respect for the extraordinary energies involved. The long-term implications of successful antimatter propulsion development extend far beyond transportation applications into fundamental questions about humanity's future in space and our relationship with energy and matter itself. Mastery of antimatter technology could mark humanity's transition from a planetary species dependent on fossil fuels to a spacefaring civilization with access to the ultimate energy source allowed by physics. The philosophical implications of controlling complete matter energy conversion rival those of nuclear technology, while potentially enabling achievements that seemed permanently beyond human reach. As research programs around the world continue pushing the boundaries of what's possible with antimatter production, storage, and control, we edge closer to a future where the theoretical capabilities we've explored tonight could become engineering reality. The technical challenges remain formidable, the timelines uncertain, and the investments required enormous by any historical standard. Yet the potential rewards, measured in terms of human capability and cosmic reach, justify efforts on scales that match the revolutionary nature of the technology itself. The antimatter engines we've journeyed through together represent more than just advanced propulsion systems or exotic physics demonstrations. They embody humanity's perpetual quest to transcend limitations, to reach beyond the boundaries that confine us to single worlds and brief lifespans, and to unlock capabilities that could reshape our understanding of what's possible in this vast universe we call home. Whether these extraordinary machines remain theoretical curiosities or become the foundation for humanity's expansion across the galaxy depends on choices we're making today about scientific priorities, international cooperation, and our collective willingness to invest in technologies that could transform not just space travel, but our entire relationship with the cosmos itself. The magnetic confinement challenges facing antimatter storage become even more complex when we consider the dynamic environment of actual spacecraft operations. Unlike laboratory storage systems that operate in carefully controlled conditions, antimatter engines must maintain perfect containment while experiencing the acceleration forces, vibration, and electromagnetic interference inherent in space travel. The magnetic field geometries that successfully trap antiprotons in stationary laboratory conditions could become unstable when subjected to the changing gravitational fields encountered during interplanetary trajectories. Spacecraft maneuvering presents particularly acute challenges for antimatter containment systems. Every course correction, every attitude adjustment, every acceleration or deceleration creates forces that could potentially disrupt the delicate electromagnetic fields holding antimatter away from material surfaces. The control systems must compensate for these disturbances in real time, adjusting magnetic field configurations faster than the contained antiparticles can respond to changing conditions. This requires computational processing capabilities that exceed current spacecraft computer systems by several orders of magnitude. The power requirements for maintaining antimatter storage during extended missions create cascading engineering challenges throughout spacecraft design. Superconducting electromagnets require continuous cooling to maintain their zero-resistance properties, demanding cryogenic systems that can operate reliably for years without maintenance. The electrical power needed for active field control could exceed the output of entire solar panel arrays, forcing designers to choose between antimatter storage capacity and other mission-critical systems like life support or scientific instruments. Backup and redundancy systems for antimatter containment must operate under principles entirely different from conventional spacecraft safety measures. Traditional engineering approaches rely on graceful degradation, where component failures result in reduced performance rather than catastrophic loss. Antimatter systems offer no such luxury, since any containment failure results in immediate and complete annihilation of the stored fuel. Multiple independent containment systems must operate simultaneously, each capable of maintaining perfect isolation, while the others undergo maintenance or repair. The thermal isolation required to maintain superconducting storage systems in the presence of antimatter annihilation. Energy creates paradoxes that challenge fundamental engineering assumptions. Heat shields must simultaneously prevent thermal energy from reaching cryogenic components, while allowing electromagnetic fields to penetrate without distortion. Current materials, science offers no solutions for this seemingly impossible combination of properties, requiring development of entirely new categories of engineered materials that exist at the intersection of superconductivity, magnetism, and thermal physics. Emergency protocols for antimatter system failures demand response procedures unlike anything in previous space mission experience. Unlike conventional spacecraft emergencies, where crews have minutes or hours to diagnose problems and implement solutions, antimatter containment failures could require responses within microseconds to prevent total loss of fuel and potentially the entire spacecraft. Automated emergency systems must detect incipient failures through subtle changes in electromagnetic field patterns while implementing corrective actions faster than any human operator could possibly react. The jettisoning of antimatter fuel during emergency situations presents unique challenges, since the fuel cannot simply be expelled into space, like conventional propellants. Any antimatter released from containment would immediately annihilate with the first material it encounters, potentially including the spacecraft itself. Emergency disposal systems must somehow transport antimatter far enough from the spacecraft to prevent damage, while maintaining containment throughout the disposal process. Proposed solutions involve magnetic field guides that channel antimatter into deep space trajectories while ensuring complete isolation from all material surfaces. Servicing and maintenance of antimatter storage systems during long-duration missions requires capabilities that exceed current spacecraft operational concepts. The complexity of electromagnetic containment systems makes them unsuitable for traditional astronaut maintenance procedures, both because of the technical sophistication required and the extreme danger posed by any containment breach. Robotic maintenance systems, specifically designed for antimatter applications, must perform complex electromagnetic field adjustments and component replacements while maintaining perfect isolation protocols. The manufacturing precision required for antimatter storage components pushes materials science into previously unexplored territories of perfection. Superconducting coils must be wound with tolerances measured in micrometers while maintaining electrical properties that vary by less than 1 part per billion across their entire structure. The magnetic materials used in field shaping must exhibit homogeneity that exceeds the best permanent magnets by factors of thousands, while operating at temperatures that would instantly destroy conventional magnetic materials. Quality control procedures for antimatter storage systems require verification techniques that can detect flaws invisible to conventional inspection methods. X-ray crystallography must reveal structural imperfections at the atomic level, while electromagnetic testing must verify field uniformity to precisions that approach quantum mechanical uncertainty limits. The testing procedures themselves pose risks since any significant electromagnetic disturbance could disrupt stored antimatter, requiring inspection techniques that can assess system integrity without interfering with ongoing containment operations. The scale-up from laboratory antimatter storage to practical spacecraft applications reveals manufacturing challenges that dwarf any previous technological transition. Current research systems store hundreds or thousands of antiprotons in magnetic traps smaller than coffee cups. Spacecraft applications would require storing quintillions of antiprotons in systems compact enough to fit aboard vehicles with severe mass and volume constraints. This represents an increase in storage capacity of more than 15 orders of magnitude, while actually reducing the size and mass of the containment systems. Advanced storage concepts explore the possibility of condensing antimatter into solid forms that could achieve storage densities approaching those of conventional materials. Theoretical calculations suggest that antihydrogen atoms could be cooled and compressed into crystalline structures held together by quantum mechanical forces rather than electromagnetic fields. These antihydrogen crystals would need to remain suspended in perfect vacuum using magnetic levitation, never touching any material surface while maintaining structural integrity under the forces required for spacecraft maneuvering. The thermodynamic properties of solid antimatter remain largely theoretical, since no experimental verification is possible with current technology. Computer simulations suggest that antihydrogen ice could exist in multiple crystalline phases, each with different storage densities and stability characteristics. The phase transitions between different solid antimatter forms could potentially be exploited for fuel delivery systems that meter precise quantities of antimatter into reaction chambers through controlled sublimation processes. Magnetic levitation systems for solid antimatter storage would require field strengths and stability that exceed any existing technology by enormous margins. The magnetic forces needed to support kilogram quantities of solid antimatter against spacecraft acceleration would demand superconducting electromagnets with current densities approaching theoretical limits. The power required to maintain these magnetic fields could consume significant fractions of spacecraft electrical capacity, while the heat generated by resistive losses challenges thermal management systems. The safety implications of solid antimatter storage create scenarios that have no precedent in human technology. Unlike gaseous antimatter that annihilates gradually as individual particles contact material surfaces, solid antimatter could potentially undergo bulk annihilation events that release enormous energies instantaneously. The explosive potential of kilogram quantities of solid antimatter exceeds that of hydrogen bombs, requiring containment systems that can prevent accidental detonation under any conceivable failure mode. Radiation shielding around antimatter storage areas must protect both crew members and sensitive electronic systems from the gamma rays produced by any accidental annihilation events. The high-energy photons created during matter-antimatter reactions can penetrate many meters of conventional shielding materials, requiring specialized radiation protection systems that add significant mass to spacecraft designs. Advanced shielding concepts use magnetic fields to deflect charged particles while relying on dense materials like tungsten or lead to absorb gamma radiation. The electromagnetic interference generated by antimatter storage systems poses challenges for spacecraft communication and navigation equipment. The intense magnetic fields required for containment can disrupt radio transmissions while interfering with magnetic compass systems and stellar reference sensors. Spacecraft designs must incorporate electromagnetic compatibility measures that isolate antimatter systems from other spacecraft subsystems while maintaining the precise field geometries needed for containment. Ground support equipment for antimatter-powered spacecraft requires specialized facilities that combine the capabilities of particle physics laboratories with traditional spacecraft processing centers. Launch site antimatter facilities must maintain the same ultra-high vacuum conditions and electromagnetic field precision found in research laboratories, while providing the rapid turnaround times needed for operational spacecraft missions. The infrastructure investments required could exceed those of major airports, while serving only a few missions per year. Transportation of antimatter fuel from production facilities to launch sites creates logistical challenges unlike any previous space mission requirement. Mobile antimatter storage systems must maintain perfect containment while traveling thousands of kilometers over potentially rough terrain. The transportation vehicles require independent power systems, backup containment measures, and communication links that allow continuous monitoring of antimatter storage status throughout the journey. The economic analysis of antimatter propulsion systems reveals cost structures that challenge traditional space mission budgeting approaches. While the fuel costs for antimatter missions could exceed billions of dollars, the reduced mission durations and increased payload capabilities could potentially justify these enormous expenditures for high-value applications. Asteroid mining missions that complete round trips in months rather than years could generate revenues that dwarf the fuel costs, especially for rare earth elements or platinum group metals. Insurance frameworks for antimatter missions require entirely new approaches to risk assessment since traditional actuarial models have no basis for evaluating matter-antimatter annihilation scenarios. The potential for total loss of expensive spacecraft systems, combined with possible collateral damage to other space assets, creates liability exposures that exceed the capacity of conventional insurance markets. Government backing or international risk-sharing agreements may be necessary to enable commercial antimatter mission development. The regulatory environment for antimatter technology development spans multiple international jurisdictions with potentially conflicting authority. Space agencies must coordinate with nuclear regulatory bodies, particle physics research organizations, and transportation safety authorities to establish comprehensive oversight frameworks. The dual-use nature of antimatter technology complicates regulatory approaches, since the same capabilities that enable peaceful space exploration could potentially be adapted for weapons applications. International treaties governing antimatter technology may need to establish verification and monitoring regimes similar to those used for nuclear weapons control. The challenge lies in distinguishing between legitimate scientific research and potentially threatening military applications, while avoiding restrictions that could hinder beneficial technology development. Inspection protocols must balance transparency requirements with the need to protect proprietary technology and maintain competitive advantages. The workforce development requirements for antimatter technology create educational challenges that span multiple technical disciplines. Universities must develop new degree programs that combine particle physics, electromagnetic engineering, cryogenic systems, and spacecraft design into coherent educational curricula. The specialized knowledge required for antimatter applications doesn't exist in current engineering programs, necessitating entirely new approaches to technical education and professional training. International cooperation in antimatter research faces the same challenges that complicate other advanced technology development programs. Nations with leading capabilities may be reluctant to share knowledge that could provide strategic advantages, while countries with limited technical resources may lack the infrastructure needed to contribute meaningfully to development efforts. Successful antimatter development may require unprecedented levels of international collaboration, similar to those achieved in particle physics research facilities like CERN. The timeline for practical antimatter propulsion development remains highly uncertain due to the unprecedented nature of the technical challenges involved. Optimistic projections suggest that small-scale demonstration systems could be achieved within 20 to 30 years, given sufficient funding and international cooperation. However, the transition from laboratory demonstrations to operational spacecraft systems could require additional decades of engineering development and testing. Conservative estimates acknowledge that fundamental breakthroughs in materials science, electromagnetic engineering, and production technology may be required before practical antimatter propulsion becomes feasible. Some critical technologies may depend on discoveries in basic physics that cannot be predicted or scheduled with confidence. The development pathway could encounter unexpected barriers that extend timelines significantly beyond current projections. The investment requirements for antimatter technology development rival those of the largest technological projects in human history. Initial research and development costs could reach hundreds of billions of dollars before practical demonstration systems become operational. Production infrastructure capable of manufacturing useful quantities of antimatter would require additional investments of similar magnitude, creating total program costs comparable to major military procurement programs. However, these enormous development costs must be evaluated against the transformational capabilities that successful antimatter technology could provide. Access to the solar system's vast mineral resources could generate economic value measured in quadrillions of dollars over subsequent centuries. The investment timeline may span generations, but the magnitude of potential returns could justify development costs that seem prohibitive by current standards. Private sector involvement in antimatter research continues to accelerate as entrepreneurial companies recognize the revolutionary potential of the technology. Startup companies are developing improved production techniques, advanced storage systems, and specialized components that could support larger development efforts. While private funding alone cannot support the full scale of development required, these smaller efforts provide crucial technological building blocks for future programs. The convergence of advancing scientific understanding, improving engineering capabilities, and growing investments in breakthrough technologies suggests that antimatter propulsion may transition from theoretical possibility to engineering reality sooner than previously anticipated. Climate change pressures, resource scarcity concerns, and renewed interest in space exploration create powerful motivations for pursuing revolutionary propulsion technologies. Space-based applications of antimatter technology extend far beyond propulsion into areas that could reshape human civilization's relationship with energy and matter. Antimatter-powered electrical generation systems could provide virtually unlimited clean energy for space colonies, industrial facilities, and terraforming projects. The complete mass-to-energy conversion efficiency of antimatter annihilation makes it the ultimate power source for applications requiring enormous energy densities in compact, lightweight systems. Orbital manufacturing facilities powered by antimatter could produce materials and products impossible to create in terrestrial environments. The combination of vacuum conditions, microgravity, and unlimited energy enables manufacturing processes that could revolutionize everything from semiconductor production to pharmaceutical synthesis. Products manufactured in space using antimatter energy could potentially be delivered to Earth markets more economically than equivalent goods produced using terrestrial energy sources. Terraforming projects that seem impossible under current energy constraints become achievable when powered by antimatter systems. Moving planetary atmospheres, redirecting asteroid and comet trajectories, or constructing massive orbital mirrors to modify planetary climates all become engineering problems rather than impossibilities when energy limitations are removed. Venus could potentially be cooled and Mars warmed using antimatter-powered climate modification systems operating over geological timescales. The scientific research applications of antimatter technology could accelerate human understanding across virtually every field of investigation. High-energy physics experiments powered by antimatter could probe fundamental questions about the nature of space, time, and matter that are impossible to investigate using conventional energy sources. The ability to create and control matter-antimatter reactions could provide insights into the earliest moments of the universe, when similar processes shaped cosmic evolution. Deep space exploration missions powered by antimatter engines could reach destinations that remain permanently inaccessible using any other conceivable technology. Direct exploration of the outer solar system's moons and dwarf planets could reveal whether life exists in the subsurface oceans of Europa, Enceladus, or Titan. Interstellar probe missions could provide direct observations of exoplanets orbiting nearby stars, potentially discovering habitable worlds or even signs of extraterrestrial life. The search for extraterrestrial intelligence could be revolutionized by antimatter-powered communication systems capable of transmitting signals across interstellar distances with sufficient power to be detected by civilizations using technology similar to our own. Antimatter-powered radio telescopes could achieve sensitivity levels that make detailed observations of exoplanet atmospheres possible, potentially detecting chemical signatures of biological activity on worlds dozens of light-years from Earth. Medical applications of antimatter technology could provide revolutionary new approaches to cancer treatment and medical imaging. Positron emission tomography already uses small quantities of antimatter for medical diagnosis, but larger-scale antimatter production could enable therapeutic applications that precisely target diseased tissues while leaving healthy cells undamaged. The perfect energy conversion efficiency of antimatter annihilation could provide unprecedented precision in medical treatments requiring extremely localized energy delivery. Materials research using antimatter-powered particle accelerators could discover new forms of matter with properties that revolutionize technology across multiple industries. Ultra-high energy collision experiments could create exotic particles and states of matter that exist nowhere else in the accessible universe. The insights gained from such research could lead to breakthroughs in superconductivity, magnetism, and quantum mechanics with applications spanning from quantum computing to gravitational wave detection. Environmental applications of antimatter technology could provide solutions to some of humanity's most pressing ecological challenges. Antimatter-powered atmospheric processes could remove carbon dioxide from Earth's atmosphere while converting it into useful products like synthetic fuels or construction materials. Ocean desalination, powered by antimatter, could provide unlimited fresh water for agricultural and industrial applications without the environmental impacts associated with fossil fuel-powered systems. Waste management applications could use antimatter annihilation to completely eliminate toxic materials that currently pose long-term environmental hazards. Nuclear waste from fission reactors could be transmuted into harmless elements using antimatter-powered particle accelerators. Chemical pollutants could be broken down into component atoms and reconstituted into useful materials through processes powered by matter-antimatter annihilation. The philosophical implications of mastering antimatter technology extend into fundamental questions about humanity's place in the cosmic order. Complete control over matter-energy conversion represents the ultimate expression of technological capability within the constraints of known physics. Species that achieve such mastery would possess godlike powers to reshape matter and energy on scales ranging from subatomic particles to planetary systems. The responsibility that comes with such enormous technological power raises ethical questions that have no precedent in human experience. Decisions about how to use antimatter technology could affect the future evolution of human civilization, and potentially the fate of life throughout the galaxy. The choices made by current and future generations about antimatter development could determine whether humanity becomes a force for creation or destruction on cosmic scales. The timeline for achieving practical antimatter applications remains uncertain, but the accelerating pace of research and the growing recognition of the technology's transformational potential suggest that significant breakthroughs may occur sooner than many experts previously believed possible. The convergence of advancing physics knowledge, improving engineering capabilities, and increasing investment in breakthrough technologies creates conditions that could enable rapid progress once critical technical barriers are overcome. The next decade will likely prove crucial for determining whether antimatter technology transitions from laboratory curiosity to engineering reality. Current research programs at major physics laboratories are making steady progress in production efficiency, storage duration, and containment reliability. Private companies are investing in specialized technologies that could support larger development efforts. Government agencies are recognizing the strategic importance of antimatter capabilities for both civilian and military applications. The international cooperation required for successful antimatter development presents both opportunities and challenges for global scientific collaboration. The scale and complexity of the technical challenges involved exceed the capabilities of any single nation, creating incentives for unprecedented levels of international cooperation. However, the dual-use nature of antimatter technology and its potential military applications could complicate collaborative efforts and create competitive rather than cooperative dynamics. As we reach the conclusion of our exploration into antimatter engines, the most powerful space technology ever imagined, we find ourselves standing at a crossroads that could define humanity's cosmic future. The physics underlying matter-antimatter annihilation offers energy densities that dwarf every other power source in the known universe, promising capabilities that could transform space travel from a barely achievable feat of engineering into routine transportation between worlds. Yet the path from theoretical possibility to practical reality remains fraught with technical challenges that push every aspect of human engineering capability to its absolute limits. The precision required for antimatter production, the complexity of electromagnetic containment systems, and the safety measures needed to prevent catastrophic accidents, all demand advances in science and technology that have no precedent in human experience. The economic investments required for antimatter development rival those of the largest technological projects in human history, while the timelines involved span decades or generations. The international cooperation needed exceeds anything previously achieved in scientific endeavors, requiring nations to share knowledge and resources on scales that challenge traditional concepts of technological sovereignty and competitive advantage. But the potential rewards justify efforts on scales that match the revolutionary nature of the technology itself. Antimatter engines could enable travel times to Mars measured in weeks rather than months, journeys to the outer planets completed in the span of single seasons, and interstellar missions that reach nearby star systems within human lifetimes rather than geological epochs. The broader applications of antimatter technology extend far beyond propulsion into realms of energy generation, materials science, and fundamental physics research that could reshape human civilization's relationship with matter and energy itself. Complete mastery of matter. Antimatter conversion represents the ultimate technological capability allowed by known physics, offering powers that seem almost godlike in their scope and implications. Whether these extraordinary possibilities become reality depends on choices being made today about scientific priorities, international cooperation, and our collective willingness to invest in technologies whose benefits may not be fully realized for generations. The antimatter engines we've explored together tonight represent more than just advanced propulsion systems or exotic physics demonstrations. They embody humanity's perpetual quest to transcend the limitations that confine us to single worlds and brief lifespans, to reach beyond the boundaries of what seems possible, and to unlock capabilities that could transform our species from planetary inhabitants into citizens of the galaxy itself. The technical challenges ahead are unprecedented in their complexity and scope, but so too are the potential rewards measured not just in scientific knowledge or economic value, but in the expansion of human consciousness across the vast scales of cosmic space and time. The universe awaits, vast and largely unexplored, filled with wonders that could reshape our understanding of existence itself. Antimatter technology may provide the key to unlocking those infinite possibilities, enabling humanity to take its place among the stars as explorers, scientists, and perhaps even gardeners of cosmic life itself. In the quiet moments between heartbeats, between breaths, between the thoughts that define our conscious existence, the future hangs in balance. Whether that future includes antimatter engines carrying human explorers to distant worlds depends on the dedication, creativity, and wisdom we bring to solving challenges that represent the ultimate test of technological civilization. The countdown has begun, not toward destruction or limitation, but toward possibilities so extraordinary they challenge our ability to imagine them fully. The most powerful space technology ever conceived awaits our mastery, and with it, the transformation of humanity from a single planet species into something magnificent beyond our current comprehension. The stars themselves watch and wait, patient as they have been for billions of years, ready to welcome us home to the cosmic community where consciousness and curiosity can flourish across the infinite reaches of space and time. Antimatter engines may prove to be the vehicles that carry us there, powered by the fundamental forces that built the universe itself, guided by the same curiosity and determination that have brought us this far in our cosmic journey. The future begins now, written in the language of physics and powered by the dreams of a species that dared to reach beyond the boundaries of the possible toward destinations that exist only in our imagination until the moment we make them real. The manufacturing complexities of our antimatter production reveal themselves most starkly when we examine the particle accelerator infrastructure required to generate meaningful quantities of fuel. Current facilities like CERN's antiproton decelerator represent technological marvels that push the boundaries of precision engineering, yet they produce antimatter at rates so glacially slow that accumulating spacecraft fuel quantities would require geological timescales under present methodologies. The fundamental physics governing antiproton creation demands that we accelerate ordinary protons to velocities approaching 99% of light speed before smashing them into dense target materials. This process converts a tiny fraction of the collision energy into matter-antimatter pairs, with the vast majority dissipating as waste heat and scattered particles that serve no useful purpose. The energy conversion efficiency hovers around 1 part in 10 trillion, meaning that for every joule of antimatter energy we capture, we must invest 10 trillion joules of electrical power. These sobering statistics illuminate why dedicated antimatter production facilities would require revolutionary advances in accelerator technology and energy management systems. Traditional circular accelerators lose enormous amounts of energy through synchrotron radiation as charged particles follow curved paths at relativistic speeds. Linear accelerator designs could potentially reduce these losses while enabling higher beam intensities, but they demand precisely aligned magnetic focusing systems extending across vast distances. The target materials used in antimatter production face challenges that stretch materials science beyond current capabilities. When relativistic proton beams strike target nuclei, they create temperatures and pressures exceeding those found in stellar cores, while generating radiation fields that would instantly destroy conventional materials. Advanced target concepts employ liquid metal jets or rotating solid wheels that distribute thermal loads across larger surface areas. But even these approaches struggle with the extreme conditions involved. Cooling systems for antimatter production facilities must remove waste heat equivalent to the output of major power plants while maintaining the cryogenic temperatures required for superconducting accelerator components. The heat exchangers operate in radiation environments that would quickly degrade conventional cooling equipment, demanding specialized designs using magnetic levitation to eliminate mechanical wear while providing thermal isolation between hot and cold regions. The electrical power infrastructure supporting large-scale antimatter production would rival that of major industrial centers. Pulsed power systems must deliver gigawatts of energy to accelerator sections within microsecond timeframes while maintaining voltage stability better than 1 part per million. Energy storage systems using superconducting magnetic loops could capture and reuse some of the waste energy from each production cycle, improving overall efficiency while reducing peak power demands. Quality assurance in antimatter production requires analytical techniques capable of distinguishing individual antiprotons from the billions of other particles created during each collision event. Magnetic spectrometers must separate antiprotons from ordinary protons with perfect accuracy, since any contamination would result in immediate annihilation during storage attempts. The detection systems operate in radiation environments that would destroy conventional electronics within seconds, requiring specialized radiation-hardened sensors and signal processing equipment. Automated production control systems must optimize beam parameters in real time to maximize antiproton yield while preventing equipment damage from excessive heating or radiation exposure. Machine learning algorithms could potentially identify optimal operating conditions that human operators might never discover, continuously adjusting hundreds of accelerator parameters based on feedback from production monitoring systems. The economics of scaling antimatter production, from laboratory quantities to industrial volumes, follows patterns reminiscent of early semiconductor manufacturing, where enormous capital investments eventually enabled dramatic cost reductions through economies of scale. The first gram of antimatter might cost hundreds of billions of dollars to produce, but the millionth gram could potentially be manufactured for thousands of dollars once production techniques mature and facilities operate at optimal capacity. However, achieving such cost reductions requires production volumes that exceed current global antimatter needs by enormous margins. This creates a classic chicken and egg problem where applications cannot develop without affordable antimatter, while affordable antimatter cannot be produced without large-scale applications to justify the required infrastructure investments. Government funding similar to that provided for nuclear technology development might be necessary to bridge this gap. International cooperation in antimatter production faces unique challenges related to technology transfer restrictions and dual-use concerns. The same facilities capable of producing antimatter for peaceful space exploration could potentially be adapted for military applications, complicating international collaboration agreements. Verification protocols must distinguish between legitimate research activities and potentially threatening weapons development while maintaining the transparency needed for effective cooperation. Space-based antimatter production offers intriguing possibilities for overcoming terrestrial limitations while creating entirely new categories of technical challenges. Solar power satellites could provide the enormous electrical energy needed without requiring terrestrial power infrastructure, while the vacuum environment eliminates atmospheric interference with particle beams. However, the complexity of operating particle accelerators in space, combined with the radiation shielding requirements for human crews, creates engineering challenges that may prove even more formidable than terrestrial alternatives. The transportation and handling of antimatter between production facilities, storage locations, and spacecraft integration sites demands logistics capabilities unlike anything in human experience. Mobile containment systems must maintain perfect electromagnetic isolation while traveling potentially thousands of kilometers over terrestrial terrain, subject to vibration, temperature variations, and electromagnetic interference from power lines and communication systems. Emergency response protocols for antimatter transportation incidents require capabilities that exceed those of any existing hazardous materials response organization. Unlike chemical or nuclear materials where accidents result in localized contamination, antimatter containment failures could release energies equivalent to nuclear explosions within microseconds. Emergency responders would need specialized equipment and training to assess and respond to antimatter-related incidents without risking further containment failures. The regulatory frameworks governing antimatter transportation span multiple jurisdictions with potentially conflicting authority over different aspects of the technology. Transportation safety agencies must coordinate with nuclear regulatory bodies, space agencies, and international security organizations to establish comprehensive oversight mechanisms. The unprecedented nature of antimatter hazards requires entirely new categories of safety analysis and risk assessment methodologies. Storage facility security measures for antimatter must address threats ranging from natural disasters to deliberate sabotage attempts while maintaining the precise environmental conditions required for containment system operation. Physical security systems must prevent unauthorized access without generating electromagnetic interference that could disrupt magnetic confinement fields. Cybersecurity measures must protect computer-controlled containment systems from malicious attacks while ensuring that safety systems remain functional even under hostile conditions. The workforce requirements for antimatter technology development span multiple highly specialized disciplines that currently exist only in research environments. Production facility operators need expertise in particle accelerator physics, while storage system technicians require knowledge of superconducting electromagnetics and cryogenic engineering. The educational pipeline for developing such expertise could require decades to establish, potentially constraining development timelines regardless of funding availability. Training programs for antimatter facility personnel must address safety considerations unlike those in any other industrial environment. Workers must understand not only normal operating procedures, but also emergency response protocols for scenarios involving energies that could destroy entire facilities within fractions of seconds. Simulation systems for training purposes must accurately model complex electromagnetic phenomena while providing realistic emergency scenarios without exposing personnel to actual risks. The environmental impact assessments for large-scale antimatter production facilities must consider effects ranging from electromagnetic interference with communication systems to potential atmospheric impacts from high-energy particle emissions. Underground construction in geologically stable formations could minimize surface environmental effects while providing natural radiation shielding. But excavation requirements for kilometre-scale accelerator complexes would create enormous quantities of displaced material, requiring careful management. Waste management for antimatter production facilities involves handling radioactive materials created during target bombardment, along with contaminated components from accelerator systems exposed to intense radiation fields. Some radioactive isotopes created during production have half-lives measured in thousands of years, requiring long-term storage solutions similar to those developed for nuclear waste management. Recycling programs for expensive accelerator components could reduce material costs while minimizing waste volumes. The energy grid integration challenges for antimatter production become apparent when considering the electrical power demands of full-scale manufacturing facilities. Peak power consumption could exceed that of major metropolitan areas, requiring dedicated transmission infrastructure and potentially new electrical generation capacity. Load balancing systems must accommodate the pulsed power demands of accelerator operation while minimizing impacts on regional electrical grids. Research and development programs supporting antimatter technology advancement operate across dozens of institutions worldwide, each contributing specialized expertise to different aspects of the overall challenge. Coordination mechanisms must ensure that research efforts complement rather than duplicate each other while protecting intellectual property rights and maintaining competitive incentives for innovation. The measurement and verification systems required for antimatter research push detector technology into previously unexplored performance regimes. Particle detectors must function reliably in magnetic field environments millions of times stronger than Earth's field, while measuring individual particle interactions with timing precision better than nanoseconds. Advanced detector designs use diamond crystal substrates and superconducting readout electronics to achieve the radiation tolerance needed for antimatter applications. Computational modeling of antimatter production and storage systems requires simulation capabilities that exceed current supercomputing resources by orders of magnitude. The complex interactions between electromagnetic fields, particle dynamics, and thermodynamic processes must be calculated across timescales ranging from femtoseconds to years, while accounting for quantum mechanical effects that become significant at antimatter scales. International standards organizations must develop new measurement protocols and safety standards specifically for antimatter technology, since existing frameworks designed for chemical and nuclear materials are inadequate for matter-antimatter systems. Calibration standards for antimatter measurements require reference materials that can only be produced using the same technology being standardized, creating circular dependencies that complicate standard development. The intellectual property landscape surrounding antimatter technology reflects the convergence of fundamental physics discoveries with practical engineering applications across multiple industries. Patent protection for antimatter-related inventions faces unique challenges, since many key concepts originated in publicly funded research institutions with complex technology transfer arrangements. Licensing frameworks must balance legitimate commercial interests with the public benefits that could result from widespread access to breakthrough technologies. Public engagement and science communication around antimatter technology must address both the extraordinary potential benefits and the legitimate safety concerns associated with matter-antimatter reactions. Educational outreach programs need to counter science fiction misconceptions while accurately conveying the real capabilities and limitations of antimatter applications. Transparent communication about safety measures and risk mitigation strategies could build public confidence without minimizing appropriate respect for the enormous energies involved. The venture capital and investment community's approach to antimatter technology reflects the tension between transformational potential and unprecedented technical risks. Early-stage investors typically seek returns within 5 to 10 years, while antimatter technology development timelines span decades. Alternative financing mechanisms, such as government-backed development programs or international consortium funding, may be necessary to support the long-term investments required. Spin-off technologies from antimatter research programs could provide near-term commercial benefits that help justify continued development investments. Advanced superconducting systems, precision electromagnetic control technologies, and ultra-high vacuum equipment developed for antimatter applications often have immediate applications in other high-technology industries. These secondary benefits could provide economic justification for antimatter research even before primary applications become commercially viable. The geopolitical implications of antimatter technology development could reshape international relations in ways comparable to nuclear weapons proliferation during the 20th century. Nations with advanced antimatter capabilities would possess strategic advantages in space exploration, energy generation, and potentially military applications that could fundamentally alter global power balances. International treaties and verification regimes may be necessary to prevent antimatter technology from becoming a source of international instability. Arms control frameworks for antimatter technology face the challenge of distinguishing between peaceful and military applications when the underlying technologies are essentially identical. Verification systems must monitor antimatter production and storage activities without compromising legitimate research programs or commercial operations. The dual-use nature of antimatter technology creates verification challenges that exceed those faced in nuclear arms control agreements. The timeline uncertainties surrounding antimatter technology development reflect both the unprecedented nature of the technical challenges and the potential for breakthrough discoveries that could accelerate progress dramatically. Historical precedents from other revolutionary technologies suggest that development timelines are often shorter than conservative estimates, but longer than optimistic projections. The Manhattan Project and Apollo program provide examples of how focused national commitments can achieve seemingly impossible goals within compressed timeframes. However, antimatter technology development faces scientific challenges that may prove more fundamental than the primarily engineering challenges that characterized previous breakthrough programs. The physics underlying antimatter production and storage is well understood, but translating that understanding into practical engineering systems requires advances across multiple scientific disciplines simultaneously. Risk assessment methodologies for antimatter technology. Development must account for consequences that have no precedent in human experience, while acknowledging the fundamental uncertainties associated with any revolutionary technology. Traditional risk analysis frameworks based on historical data and statistical models cannot adequately address scenarios involving complete matter-energy conversion. New approaches combining theoretical physics models with engineering safety analysis may be necessary to develop appropriate risk management strategies. The insurance and liability frameworks required to support antimatter technology commercialization present challenges that exceed the capacity of existing commercial insurance markets. The potential for catastrophic losses involving energies equivalent to nuclear weapons creates liability exposures that may require government backing or international risk-sharing arrangements. New categories of insurance products specifically designed for antimatter applications may need to be developed. As our exploration of antimatter engines draws toward its conclusion, we find ourselves contemplating a technology that represents both the ultimate expression of human scientific achievement and perhaps our greatest test of technological wisdom. The physics underlying matter-antimatter annihilation offers energy densities that approach the theoretical limits allowed by natural law, promising capabilities that could transform humanity from a planetary species into a truly cosmic civilization. Yet the path from laboratory demonstration to practical application remains fraught with challenges that demand advances in science, engineering, and international cooperation on scales that have no precedent in human history. The technical obstacles are formidable, the safety requirements unprecedented, and the investments required enormous by any historical standard. But the potential rewards justify efforts that match the revolutionary nature of the technology itself. Antimatter engines could enable exploration of the outer solar system within timeframes measured in months rather than decades, while interstellar missions that once seemed impossible could be completed within single human lifetimes. The broader applications of antimatter technology extend into realms of energy generation, materials science, and fundamental physics research that could reshape civilization's relationship with matter and energy. The choices being made today about research priorities, international cooperation, and technological development will determine whether these extraordinary possibilities become reality or remain forever confined to the realm of theoretical physics. The antimatter engines we've explored together represent more than advanced propulsion systems or exotic scientific demonstrations. They embody humanity's perpetual quest to transcend limitations, to reach beyond the boundaries that confine us to single worlds and brief lifespans, and to unlock capabilities that could carry our species to destinations that exist today only in our most ambitious dreams. The universe awaits, vast and largely unexplored, filled with wonders that could transform our understanding of existence itself. Whether antimatter technology provides the key to unlocking those infinite possibilities depends on our collective wisdom in navigating challenges that represent the ultimate test of technological civilization. In the balance hangs not just the future of space exploration, but potentially humanity's transformation into something magnificent beyond our current ability to imagine. The stars watch and wait, as they have for billions of years, ready to welcome us home to the cosmic community where consciousness and curiosity can flourish across the infinite reaches of space and time. The most powerful space technology ever conceived awaits our mastery, and with it, the destiny we choose to create among the endless possibilities of the cosmos. The international space law implications of antimatter technology development raise fundamental questions about sovereignty and jurisdiction that extend far beyond Earth's atmosphere. Current space treaties were drafted with chemical and nuclear propulsion in mind, never anticipating the energy densities and capabilities that antimatter systems could provide. The potential for antimatter-powered spacecraft to reach any location in the solar system within weeks creates scenarios where traditional concepts of territorial control become meaningless. Consider the enforcement challenges that arise when spacecraft can change their trajectories instantaneously using antimatter thrust. Unlike conventional vessels that must follow predictable orbital mechanics, antimatter-powered craft could alter their destinations without warning, making it impossible to track their intentions through trajectory analysis. This capability fundamentally undermines existing frameworks for space traffic control and collision avoidance systems that depend on predictable flight paths. The weaponization potential of antimatter technology forces us to confront uncomfortable realities about the dual-use nature of scientific advancement. While our focus tonight has centered on peaceful exploration and scientific discovery, the same production facilities and storage systems that enable interplanetary travel could potentially be adapted for military applications with devastating consequences. The energy density of antimatter fuel makes it inherently dual-use technology, where the distinction between propulsion system and weapon becomes a matter of engineering application rather than fundamental capability. International monitoring systems would need to distinguish between legitimate scientific research and potentially threatening military development programs without stifling beneficial technology advancement. The verification challenges exceed those faced in nuclear arms control, since antimatter production facilities could theoretically be much smaller and harder to detect than uranium enrichment plants or plutonium reactors. Satellite surveillance systems designed to monitor nuclear activities might be completely inadequate for detecting clandestine antimatter programs. The economic disruption potential of antimatter technology extends into sectors that seem completely unrelated to space exploration. Energy markets would face fundamental transformation if antimatter-powered generators could provide unlimited clean electricity at costs competitive with fossil fuels. Transportation industries could be revolutionized if antimatter systems prove applicable to terrestrial vehicles, enabling aircraft that operate more like spacecraft than conventional airplanes. Mining and resource extraction industries would confront existential challenges if asteroid belt resources become accessible through antimatter-powered cargo vessels. The platinum group metals contained in a single metallic asteroid could exceed Earth's entire known reserves, potentially crashing precious metal markets while providing unprecedented abundance of materials critical for electronics and chemical processing. Traditional mining companies might find their terrestrial operations completely obsolete overnight. The agricultural implications become apparent when we consider the energy-intensive processes required for food production in space colonies. Antimatter-powered life support systems could enable agricultural production in environments where solar energy is insufficient, such as the outer solar system moons or underground facilities on airless worlds. Controlled environment agriculture using antimatter energy could potentially achieve crop yields that exceed terrestrial farming while requiring no soil, pesticides, or natural rainfall. Pharmaceutical manufacturing in space offers unique advantages that become economically viable only with antimatter-powered transportation systems. The microgravity environment enables production of protein crystals and other biological materials with properties impossible to achieve on Earth. Complex medications that require ultra-pure environments could be manufactured in space and delivered to terrestrial markets more cost-effectively than equivalent products made in Earthbound facilities. The telecommunications revolution, enabled by antimatter technology, could transform human communication across interplanetary distances. Current spacecraft depend on solar panels for power, limiting the strength of radio transmissions as they travel farther from the Sun. Antimatter-powered communication satellites could maintain full broadcasting capability throughout the solar system, enabling real-time communication networks that connect Earth with colonies on Mars, Europa, or Titan. Educational systems would require fundamental restructuring to prepare students for careers in antimatter technology, development, and application. Traditional physics and engineering curricula barely touch on the specialized knowledge required for electromagnetic confinement systems, particle beam dynamics, and superconducting technology operating under extreme conditions. Universities might need to establish entirely new departments dedicated to antimatter engineering, combining theoretical particle physics with practical engineering applications. The research infrastructure required to support antimatter technology development would transform the scientific landscape in ways comparable to the construction of major observatory networks or particle accelerator facilities. International collaborations spanning dozens of institutions would need to coordinate research efforts across multiple continents while sharing incredibly expensive equipment and expertise. The scientific workforce required could exceed that of entire existing research fields. Medical applications of antimatter technology extend far beyond current positron emission tomography systems into therapeutic realms that seem almost magical by today's standards. Antimatter-powered particle accelerators could enable cancer treatments with unprecedented precision, delivering therapeutic radiation doses directly to tumor cells while leaving surrounding healthy tissue completely unaffected. The perfect energy conversion efficiency of antimatter annihilation could provide the precise energy control needed for surgical applications that require atomic-level precision. Diagnostic imaging using antimatter could revolutionize medical practice by providing three-dimensional views of biological processes in real time. Current medical imaging systems are limited by the energy available from conventional sources, but antimatter-powered scanners could achieve resolution and sensitivity levels that make current technology seem primitive. Early detection of diseases at the cellular level could become routine, potentially preventing conditions before symptoms even appear. The environmental restoration applications of antimatter technology could address some of humanity's most pressing ecological challenges. Atmospheric processing systems powered by matter-antimatter annihilation could remove greenhouse gases from Earth's atmosphere, while converting them into useful products like synthetic fuels or construction materials. Ocean cleanup projects could use antimatter energy to power filtration systems that remove plastic pollution and toxic chemicals on scales that dwarf current capabilities. The universe holds its breath tonight, waiting to see whether this extraordinary technology will remain forever locked in the realm of theoretical physics or become the foundation for humanity's greatest adventure among the stars. We've journeyed together through the mind-bending physics of matter-antimatter annihilation, explored the staggering engineering challenges that push every boundary of human capability, and glimpsed the transformational possibilities that could reshape our entire relationship with the cosmos itself. From the microscopic precision required to trap individual antiprotons in electromagnetic bottles to the vast infrastructure needed for practical fuel production, antimatter engines represent both our species' most ambitious technological dream and perhaps our ultimate test of scientific wisdom. The path ahead demands investments that rival the largest projects in human history, international cooperation on unprecedented scales, and breakthroughs that could redefine what we thought possible. Yet the rewards justify every challenge we've explored tonight. Mars in weeks rather than months, the outer planets accessible within single seasons, interstellar journeys completed within human lifetimes rather than geological epochs. These aren't fantasies from science fiction, but engineering possibilities that await our mastery of the most powerful energy source the universe allows. Whether antimatter engines carry humanity to the stars depends on choices we're making right now about research priorities, global cooperation, and our collective courage to pursue technologies whose benefits may not be fully realized for generations. The countdown has already begun toward a future where the boundaries between Earth and cosmos dissolve completely. Until we meet again on another cosmic journey, keep looking up, keep questioning, and remember that the universe itself is waiting to welcome us home to destinations that exist today only in our boldest dreams.